So last time we started to look at different kinds of, like, up until now in this course, we have always talked about algorithm for vertex cover, okay? And the algorithm which we have seen up until now was parameterized by K, parameterized by N, okay? Where K is solution size, N is number of vertices in the graph, okay? And okay, and what we know is K is less than equal to N. And then we started to make some sort of taxonomy of smaller and smaller parameters. And the first question which we studied was, we said that maybe look at the base, polytime base cases, and maybe we should try to study modulator to that, parameterized by modulator to that. So let's look at vertex cover problem itself, okay? But now input is G, K, L, okay? Now we will fix what parameters should be. And the question is, as always, does G have a vertex cover or size at most K? Okay. Now, what is this L? Okay. Now, what is this L? So first, L is like, we said that maybe let's parameterize this problem by what I call, these are called modulator. Okay. So what is the meaning of modulator? Modulator is generally used for the set of vertices which has some property. So when I say modulator to degree 2 graphs, means set of vertices whose deletion is deletion leads to graph of degree at most 2. Okay. So now, okay. So now let's call this modulator modulator to degree 2 graph. So let's what symbol did I use? I don't remember now. Okay. So let me use the fact modulator to degree 2 of G. So what is the modulator degree 2G? Is minimum number of vertices whose deletion takes us into what do you call a modulator to G is set of vertices in G whose removal gives us a graph of degree at most 2. Now, what we know about this, that mod 2 of T is less than equal to vertex cover of G. Am I right? Is this statement okay? Like, is this fine with everybody?
Yes.
Okay. Now, what is our objective? So we want to design a vertex cover algorithm parameterized by F of mod D2 of G times n to the power big O. Okay. So now, just to be a part of decision version of the problem, we will say, so there are like various ways you can ask this question. Okay. So now I can say, what is the parameter of L? Where L, so now, so I want to mean that L is like mod D2 of G. Okay. Now, various ways this question is phrased. So, given a graph G, okay, you can either say that look, modulator D2 modulator of G is greater than L, or return a vertex cover of size at most K in time F of L times n to the power big O. Okay. So it's possible that I'm saying that, look, what is L? L is my presumably size of mod D2 of G. But if the mod D2 of G is large, okay, then you can say to me, look, so in some sense, these are promised question. What is a promised question? In the sense, I have promised you that the graph I have given you has a modulator of size, degree 2 modulator of size at most L. So that is my promise to you. Okay. So if that promise is fulfilled, then you have to return me a vertex cover of size at most k in running time f of L poly n. Or you can say, look, you told me that you promised me that this graph has degree 2 modulator of size at most n, but hey, look at this. This is a witness which tells me that it is not a modulator of this. So this is one way we can phrase this question. Okay. So these are called oblivious. Like I have not given you modulator. So these are like oblivious. Okay. So these are oblivious format of question. Okay. Now there is some non-oblivious format of question, which is a slightly easier question. Okay. To state. Okay. So now let me say non-oblivious format of a question. Okay. So now what I'm given to you, I will also give you, these are like a non-oblivious format of question. I give you a set S such that G minus S has degree at most 2. And what is my parameter? Parameter is L size of S. So this is non-oblivious. Okay. This is non-oblivious. Okay. So what I mean by non-oblivious is that I have given you a modulator, right? So there is like not only promise that I'm giving you graph G and here is your modulator. Can you take the help of this to come up with a vertex cover of size at most k, right? So it should remind you that of the vertex cover question when we were doing about this compression question, right? So to solve vertex cover, we took help of modulator to itself, right? So I have generalized this notion and say, look, I will not give you vertex cover per se for a help, but I have a set S such that if you delete this, then degree is at most 2. Can you take help of this? So this is non-oblivious. Why? Because I have given you set S. And look at the non-oblivious question. I do not give you set S. I only give you guarantee in the sense that I promised you that there is a vertex cover of size at what do you call degree 2 modulator of size at most L. So, and if indeed the promise is met, you should output me a vertex cover of size at most k if it exists in running time f of the modulator. Okay. And if it is not, then you should immediately tell me that this holds. Okay. Is that fine? Is the question clear to all of you? Okay. Okay. So let's do a party today. Okay. Party like okay. So let's see. Okay. So fine. Okay. Let's see. Sanjay, can you hear me?
That was not me.
No, I'm asking you.
Oh yeah, I can hear you. Yes, yes.
Okay, no. So here's a question for you.
Great.
Okay. Okay. So till Sanjay and I are solving oblivious, non-oblivious question, others think about the oblivious format of question. This question. So what do you think? Do you know an algorithm for this problem? For this format where S is given to you. Simple answer is that all of you know the answer. Like we have, like even if I had given this question in your exam or something, like it wouldn't take you more than a few minutes to solve it. After what you have seen in the course, this format of question where S is given.
So we can guess the 2 power L subsets of S, and the remaining graph, the degree will be at most 2, and we can guess the intersection of a vertex or a size at most k with S and find the remaining.
Okay, so if I have to understand the question, what you are saying to me is that, okay, let's look at this your S, and this is basically cycles and paths, right? Because this is degree 2 graph. Am I right? Okay. Now what you are telling me is that let's do one thing. Let's guess which subset of S of size at most k, right? So I'm guessing. So suppose X is my potential vertex cover of size at most k. Am I right? So what Sanjay is doing? He's saying, okay, let's take Z, guess Z, which is X intersection S. So this is his Z. Am I right? Okay, then what are you doing?
Now, of course, the remaining X minus Z should be an independent set, and
what is X minus Z?
X minus Z. Sorry, S minus Z. Sorry.
Okay.
S minus Z.
So what he is saying is that if Z is valid guess, then S minus Z is an independent set. Am I right?
Yeah.
Suppose it satisfies this property. Now what? So to X union X intersection S, what else should I add?
Neighborhood of S minus Z.
Okay, so what he wants to add is neighborhood of S minus Z.
Yeah.
Right?
And after that, we may need to add some more edges.
So now what he says that, look, and for these guys, let's add some vertices which are neighbor to these guys. Am I right?
Yes.
Okay. Then after I have done this, what is left?
Graph with degree at most 2.
Okay, so call this W. Now look at G minus W. G minus W, maximum degree of G minus W is at most 2. Is that fine with everybody?
Yes.
Okay. If that is fine with everybody, then what can be computed in G delta, like what can be computed in G minus delta, G minus W? We can compute minimum vertex cover of G minus W in polytime. Is that fine? Call this set Q. So what I'm going to return? I'm going to return X intersection S, right? Plus neighborhood of S minus Z plus W. Clearly this is a vertex cover, and if this has size, if this size is at most K, you say yes. And if you fail for every guess of Z, then return no. Is that fine? Is this algorithm fine to everybody?
So do you add W or do you add some subset of vertices in G minus W?
So you add Q instead of W, right?
Sorry,
in the
sorry.
last line.
Yeah, that's my mistake. What was W anyway? Oh, n of S minus Z was W. I called this W. Okay. Yes. Right. You're right. I add this. It was my mistake. Is this fine? Is the algorithm fine with everybody? Yes, then please put +1. Okay. What's the running time of this algorithm? What is the running time of this algorithm?
2 to the power L times polynomial in A.
Okay. Rather, I going from 0 to k, L choose I, n to the power big of 1, which is at most 2 power L times n to the power big of. Funny, no? Okay. Is everybody happy with this algorithm? Okay. Okay. So I think here's I don't know whether this is an open question or not, but here's a question number 1. Devise 2 minus epsilon to the power L to the power n to the power big O of 1 time algorithm for vertex covered parameterized by modulator, degree 2 modulator. Okay, you understand the question. And I'm talking about non-oblivious setting. Okay, and I'm only talking about non-oblivious setting. In the sense, I gave you this set S. Okay, S is given as part of the input. That is, modulator is given as a part of input. Okay, is that fine to everybody? As a question, I'm not asking answer.
Yeah.
Okay, fine. Now let's go back to the oblivious question. Okay, now imagine that I did not give you S. What can we do? Okay, this is parameterized by lots of people write modulator to degree 2 of degree 2 modulator. Okay, now, so what is the question now we want to say? Either report that modulator to 2 of G is strictly greater than all, or find a vertex cover of size at most k in time f of L times n to the power. Is this fine? Is the goal clear of this question? Okay.
So when
Hello, one by one, please.
I still don't understand the difference between oblivious and non-oblivious versions.
In oblivious version, S is not given to you. I just gave you a graph.
Yeah. Okay.
That's it. That's a difference.
Okay.
Right? And in the non-oblivious version, I also give you the set S. So there's a very big difference. Right? Look at the oblivious, non-oblivious version, right? What is input? Input has G, K, S such that this.
Okay.
Okay. And in non-oblivious, just graph is given to you and number K, comma L is given to you. And you would say, look, I think this graph has a modulator of size, degree 2 modulator of size at most L. Okay. But what you can do, you take this graph G and say, hey, look, I mean, if your promise is fulfilled, like a complexity theory questions, right? If the promise is met, I will give you an answer. If the promise is not met, even then possibly I can give you an answer. But there are times when I can say, look, here is a problem, right? Your promises are not met. But whenever my promise is met, you always output correct answer. Is that fine?
Yeah.
Okay. So what do you think? How can we go about it?
Okay, so for the first case, like modulator is greater than L, does that mean that no vertex cover of size K?
No.
No,
I'm
we are
not saying
this
that.
or this, so that
Yeah. No, I don't know about that. There could be a vertex cover of size at most K. But all I'm saying that, look, you are not meeting your promise. That's it. And I had my witness that you are not meeting your promise.
Okay.
Say, for example, you put L equal to 1. Okay. And your vertex cover is like unbounded. Okay. You expect me to answer that question in poly time then, right? If I give you f of L poly time in this algorithm, that it has a vertex cover of size at most K or not, right? Right? Then you can put L equal to 1 and you can keep changing K. And you will get Is this fine?
Yeah.
Okay.
So
So
I have a question.
please ask.
When you say the promise, it means the promise of outputting like vertex cover size at most K, right?
No. Promise is that the graph has a property that it has a degree 2 modulator of size at most L. That is my promise. That my promise is that my graph is special.
Okay.
So what is my promise? That promise is that, so for example, I can promise to you that my graph is planar. Okay. But I do not give you this any. I said, look, here's my graph. If it is planar, you output me. If it is not planar, don't care. Don't worry about it. So it is of that kind of algorithm. So if look at a graph G, if it does have a modulator of size at most L, I return you a vertex cover of size. Suppose it does not have a modulator of size at most L, then I can also return a vertex cover of size at most K in this case, but I can also tell you that you're cheating if this graph does not have a modulator to degree 2 graph of size at most L. Okay, so my promise is, so think of this way, right? Here, my promise is so promise is like, or forget about it, given G, K, L, okay? Either you have to tell that report that the modulator to degree 2 graph is at least L, okay? Or if it is not, then you have to find me a vertex cover size at most K in time this much. That's it.
Saket?
Yes.
So in this case, the additional check that you do is that the promise is met or not. And
No, I don't check.
otherwise, how do you know that like in the given graph modulator of G is greater than L or not?
I mean, algorithmically on the way, I can probably figure it out.
Okay.
Right? I mean, you get my point. Like all I'm telling you that, look, if it is at most L, I will definitely give you a solution of size at most K if it exists. Okay. But if it is not, sometimes I will give you a vertex cover of size at most K if it exists, or sometimes I can also tell you that, hey, you're cheating. Your graph Here's a set of vertices which, or I will give you some bitness which will tell me that this graph has degree 2 modulator of size strictly more than L. Okay, so what I mean to say that given a graph G, okay, look at a graph G and look at L, look at an L, okay. What are the two possibilities? G has a degree 2 modulator of size at most L, right? Or not?
Saket,
Yes.
I think the standard definition of promise problem is that if it does not have that promise property, then the algorithm can basically say anything.
Yeah, but in my, all you are allowed to say is that it doesn't meet the promise. Anything always means that you can say that you are not meeting the promise.
Or also if actually it has the property that the kind of property you want to find, that's a vertex cover of size k, it could also give a vertex cover of size k if actually the graph does have a vertex cover, meaning the algorithm is not required to be correct on that input.
No, that, like there are different ways of defining promise. Okay, so this is my promise. If the promise is met,
Yes,
okay,
then you absolutely have to answer correctly.
yes. If it is not met, then you tell me that you have not met.
Okay, so you want a certificate that the promise is not met.
Yes. How should I trust you?
Okay.
Okay. So G, if G has degree 2 modulator of size at most L, then must return, if this algorithm must return a vertex cover of size at most K if exists one. Okay. In this case. And what is the running of time of this? Is this. In this case, you can say, in this case also, you can return a VC of size at most K if exists in time f of L n to the power big O of n. Or you can also say that G is more than L. Okay. Is this fine? Look, in the second case, when the condition is not met, it is possible that your algorithm, look, that's a good thing about oblivious algorithm, right? That they're just given a graph G, they work, right? So all I'm able to prove about these algorithms that when the input is of this nature, this algorithm definitely returns the way I desire. But when input is of not this nature, it can sometimes return an answer correctly, or sometimes it can just also return you that your input is of not that type, right? So for example, I have an algorithm that, look, I will give you a very good example, okay? Okay, so this will be much more instructive. You know what is called unit disk graph? Okay, unit disk graphs. Okay, I'm digressing, but it is important to know this. Okay, what is unit disk graphs? So basically, there are n unit disks in plane. Okay, unit disk means of diameter 1 or radius 1, whatever you fix it, right? Okay, and how do I define a graph given these disks? I have vertex for each disks, vertex for each disk. Okay, and if two disks intersect, you add an edge. Is that fine with everybody? The definition of unit disk graph? Is the definition of unit disk graph clear to everybody?
Yes.
Okay.
Yes.
Okay. Now, suppose input is a graph G given in say adjacency list format or matrix, whatever. Okay. And testing whether G is unit disk graph or not is not polytime. It is an NP hard question. You get my point? Now there are algorithms for, but what we know about this, that click is p times solvable on unit disk graph. Okay. So now what is the meaning of p times solvable on unit disk graph? It means there could be meaning of t. I not only tell you, I give you unit disk representation. I give you, not only I give you graph G, I also tell you, here are the disks in the plane. Okay. Disk representation is given. And so now you basically not only get given a graph G of this, but, or I give you a graph G, it returns a maximum size click in polytime. You get my point? It returns maximum size click in polytime. Okay. And sometimes it takes much more time than, okay. So what happens is that, okay. So now here's my input, graph G. Okay. And and what does it outputs? It outputs a maximum click of G. Okay. It's an algorithm that will always works. Okay. And it always outputs, like it is supposed to output a click, some click of G in polytime. Okay. In polytime. Okay. It will output or whatever. Okay. So suppose it always outputs a maximum click of G in some time. Okay. It could be polytime, it could be exponential time. I don't know, but it always returns a maximum click of G. Okay. But I can prove if G is actually unit disk graph, then running time of the algorithm is p time, like some n to the power 3, for example. Right. So now what I can do this to this algorithm, right? I will run up to n cube time. If it succeeds up until then, I'm happy because I got a maximum click, right? If it goes beyond n cube, what I can do, I can just terminate this algorithm and say, hey, your graph is not unit disk. You understand my point? Right? If I can prove that here's the property that if G is unit disk graph, then running time of this algorithm is at most n cube. Okay. So now what I will do, I will take this graph, take this algorithm, feed him G. I said run. Okay. The moment the running time goes beyond n cube, I'll just stop. And what I can say, hey, look, your whatever input you have given me is not unit disk graph. Is that fine? So when I stop at n cube plus 1 step, I'm guaranteed that input is not a unit disk graph. But if I stop till n cube, am I guaranteed that every graph that it stops on is unit disk graph? No. It could be that for some other graph, this algorithm is able to find maximum click in polytime. All this is guaranteed that it will definitely find maximum click if the input graph is unit disk graph. Right? So these are called robust algorithm. These are called oblivious algorithm. Like they do not know what G is, right? But if G is given with some interesting property, it is able to do the job nicely. And here nicely meant polynomial time. Okay. So this is the kind of algorithm is also called robust algorithm and things of this nature. Okay. So these are called non-oblivious algorithm. So for example, whenever we work on unit disk graph or disk graph, we want our algorithm that does not ask me for the representations, right? It just get a graph as a adjacency list representation or a matrix representation, and whatever problem I want to solve, it is guaranteed to solve that in this running time. That's it. So in that sense, this is a robust algorithm or non-oblivious algorithm. Okay. So I hope, because we cannot hope that given a graph G, test whether it is unit disk graph or not in polytime. We cannot test, because testing whether the input graph is unit disk or not is not polynomial. Okay. I hope this clarifies a little bit more.
Okay, you said it is called non-oblivious. I think it's called oblivious because it's oblivious to the fact that G.
My mistake. Yeah.
But oblivious is like when it is blind to a certain fact.
So this is oblivious algorithm. Yes. Okay, so in this, people try to design. So for example, first thing is, okay, fine, if you're given me, if first people try to design non-oblivious algorithm, and then they try to design oblivious algorithm. Okay, and oblivious algorithm is always more desirable than non-oblivious algorithm. Okay, is that fine to everybody? Like this little discussion, so that we can go back to our algorithm. Okay. 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 So now let's go back to our so what can we do for this oblivious algorithm? Any idea? Okay.
If I could find the mod D2G of size less than L in f of L times n to the power of 1 time, then I can apply the earlier algorithm.
Yeah, that's also a good idea.
And then,
Yeah. So the good idea number 1 is excellent. Okay. If there exists an algorithm to test, okay, if there exists an algorithm to test whether there exists a modulator, or let's say degree 2 modulator to G running in time f of L n to the power big of 1, then I can first run this algorithm. If there is a modulator of at most L, great, then I run the algorithm which we did before. And or if it is more than L, then I say, hey, this is not that. Okay. So what is this model algorithm will do? So basically he says, what is he saying? If the following problem is FPT, so let's write down, okay. Degree 2 modulator problem. So what is the degree 2 modulator problem? Input is G, say S, okay. My parameter is S, and the question is this classical parameterized question. Does G has a set S of size at most S such that G minus S has degree at most 2. Okay, and what's the running time of algorithm we are looking for? We are looking for this. So now what does Ajay wants is that he wants to run algorithm for, so he says run algorithm for degree 2 modulator with S equal to L. Okay. If yes, then we have a set S of size at most L such that maximum degree of G minus S is 2. Okay. Then what is he saying? Now run non-oblivious algorithm. Right? So the running time of this algorithm is going to be what? So running time of this algorithm is going to be, if this is f of L. So this is going to be f of L n to the power big of 1 plus 2 power L big of 1. Is that fine with everybody? Is this algorithm okay? Assuming whatever he said.
Yes.
Okay. Can you design an algorithm for degree 2 modulator then? Okay. So now we can go back. Now this is our question, right? Like, let's implement this. Okay. Start. Can we design an algorithm for this problem? Again, all of you know an answer. There's absolutely no one there who does not know the answer. Suppose I have a vertex V. It has, suppose these are his 3 neighbors. There could be more neighbors. I don't know. There could be more neighbors, but I just pick up these 3 guys. What can I say about this?
We need to at least remove one neighbor.
A, B, C, D. Can A, B, C, D, all of them survive?
No.
How many of you agree to this point? That S intersection A, B, C, D Kushal, do you agree? What is an ultimate aim? Our ultimate aim is that to have a graph where maximum degree is at most 2. So if A, B, C, and D, all of them will survive at the end after deleting, then what is the degree of A? It is 3, which means at least one of them must go into my solution, which implies, now do we have an algorithm?
4 to the power.
Right? So this is an algorithm we made, right? If such a thing we are able to prove, then we were able to show these kind of algorithm, right? So now don't look at all the neighbors of these. There are many, I don't care, but I pick up only 4 of them. So it's clever. It's like, otherwise all I can say, but then if you take more vertices, you can say more vertex I will pick up, right? All but 2 must go. Okay. So this is anyway. So this is like 4 to the power S algorithm, not K, S algorithm. Right? So we did design an algorithm. Okay.
Would 3 neighbors not satisfy?
What do you mean by 3 neighbors?
I mean, instead of 4, even if we'll take 3 neighbors, then we know that.
We have only 3 neighbors, no? B, C, D.
Oh, okay.
Right? A and B, C, D. Okay. It's just that because it's possible that A could also go into the solution, right?
Yes.
Right? So, yeah. But there are several possibilities, right? If this vertex had larger degree, say 4 or 5, and if A does not go, then several of them can go. Okay. At least 2 has to go. So, okay, I'm not trying to optimize anything. Okay. So now, what did we get an algorithm? So we got an algorithm now. And so now we got an oblivious algorithm. Okay. We got an oblivious algorithm, which is 4 to the power L to the power N to the power big of 1. And this, which is 4 to the power N. Okay. It is funny, no? Is that it's to get to a non-oblivious algorithm, we are spending more time than solving the problem itself. But it is kind of conceivable that this is how it should happen. Okay, so this was good idea 1. What else could we do to solve our oblivious problem?
If we have some approximation algorithm to find a modulator, then we can use the approximate solution instead of modulator like optimal.
Okay, so okay, so here's a good idea number 2. What is a good idea 2? Apply approximation algorithm. Okay, so suppose we have factor, say, alpha approximation algorithm running in p time. What can we do this then?
So in that case, we'll have a modulator of size at most alpha L.
Why?
Because we have alpha approximation algorithm, so we can use this algorithm.
Okay, so suppose this algorithm, let's call this algorithm A. Run A on G and obtain a set S. Now what should I do? I got this set S.
So now its size is at most alpha times L.
If this is then
now we can apply our old idea and just look at the all possible subset of this.
Then apply non-oblivious algorithm. Okay, excellent. So in this case, my running time is n to the power big of 1, because that's what we took. And now it would be 2 to the power alpha times n times n to the power big of 1. Okay, and if this is this, then what?
We can, in that case, we can say that it is strictly greater than L.
Okay. And if this is the case, then say that there is no degree 2 modulator of size at most L. Madhumita, is that fine?
Yes.
Right now, we are not explicitly finding it, right? But there are situations where we can tell that there is a modulator of this. right? But we are solving this problem even when there are cases when the modulator is, I don't know whether modulator of size L is there or not. So when in the first case, all I know that my modulator is size at most alpha L, but it's possible that minimum size modulator has size 2L actually, or 3L. It's just that my approximation algorithm returned a solution of size at most 4L, right? Is that clear? Look at in the first case, when an approximation of them returns you a solution of size at most 4L, for example, then all you know that the solution size is at most 4L, nothing more than that. Right? Okay. Anyway, so is this algorithm clear to everybody? Okay. Fine. If that is the case, can we implement this? Okay. Making A. How will we make A? Okay, so Madhumita had a question that what value of alpha can it be? Okay, so that's a good question. What happens if alpha is something which depends on, say, alpha is some function of L? Will anything will happen?
Then that's fine. 2 to the, it still remains 2 to the function of L.
Correct. So that much power I can definitely give.
Okay.
So alpha could be as large as some function of L. Okay. Okay, but how do we make this A in our case? Again, it's not hard. We just need.
If we greedily delete highest degree vertices.
So what will happen?
Yeah.
That is not even a good approximation other than Sonic for vertex covered.
Yeah.
Deleting a vertex. But go back to the algorithm which I showed you. S intersection ABCD equal to 1. This also tells you something interesting, no? Delete all ABCD, then what will approximation factor of that algorithm will be? This is also gives you an approximation algorithm, which I never told you.
Yeah,
You know that S intersection ABCD is at least 1. Take all ABCD, delete it from the graph. Every time I know that my S intersect with the set which I deleted, right? And these are distinct vertices because these are distinct objects. It's like a packing. Like you do a vertex disjoint packing of claw. Okay. Is that fine? Packing of these guys. Okay. So notice G has maximum degree 2, if and only if G does not contain this as a subgraph, as a subgraph. Is that fine?
Yes.
Yeah. So now if this is then what is this? Find the set of vertices which contains this. Delete in G. So suppose I caught a copy H1. Now in G minus H1, another one. So on and so forth until you can't do it. Okay. Now what you know from any optimum solution will from any S must select one vertex each from each copy, each vertex disjoint copy, right? So what do you know? Cardinality of S is at least L, where L is a copy you got. And what are you returning of size at most 4L? So what factor approximation did you get?
4.
4. Is that fine with everybody? Is this algorithm fine with everybody?
Yes.
Okay. Okay. So there is factor for approximation to degree 2 modulator problem. Is that fine? Okay. Hi, Sayani. Is there better thing known for this?
I think 2.
2 is known. Okay.
2 is known.
Okay. Okay. So what I told you is 4, but as Sayani tells us that there does exist a factor to approximation for this. Okay. Fine. Okay. So we learned 2 strategy. Okay. What is strategy 1? Design Madhumita, why it is 4L? Because look, my process stopped after L steps, right? H1 to HL. Right? Now take all the vertices in here, all the vertices here, all the vertices here, all the vertices here. If you delete them, is there any H?
Yeah, I
That's it.
got it. Yeah.
This is something which I also told in graph theory class a couple of days back. Okay. So what is the strategy 1? Design FPT algorithm, or FPT approximation also can work, algorithm for the modulator. Okay. And secondly, like designed P time approximation. Yeah, I mean, same thing. Okay. And then run non-oblivious algorithm on the problem. Okay. So now let's go back and okay. So now we are changing gears and picking up slightly difficult problem. Okay. So now again, our objective is to solve vertex cover. It never changes. Okay. Our objective is to always solve vertex cover in this course. Okay. We don't want to solve anything else. Anything else is just a help to solve it. Okay. Input is J. K, and S. But now, what is the property of S? G minus S is a forest. Okay. My parameter is L, size of S. Question: does G has a vertex cover of size at most K? This is, let's call it non-oblivious. This is non-oblivious, right? Do we know an algorithm for this question?
Yes. Yes, you can design an activity.
Okay. What is an algorithm? I think Sanjay has ran away, so I was searching him. He's not around. Okay. Okay. So what algorithm?
Same as Sanjay told earlier.
Exactly, right? Nothing changes in that algorithm, right? You, okay. Here is your S, here is your forest, right? You guess who goes into the solution, right? And for the remaining guy, look at their neighbors, right? So this plus this, and after you delete it, solve the problem in poly time on the forest. Nothing changed, right? So this seems to be a routine. Whenever I have an oblivious question, like we are able to design an algorithm running in time. Okay, is that fine? Okay. Let's do one more non-oblivious question, and then we will do let's see if okay. Now, if I put here is bipartite. Okay. So the graph looks like this. Now, can we do this?
Same thing.
Exactly.
Same thing.
Yeah. Okay. But try to do better than 2 power L for either of this, and then that's a fun thing. I only thing which I can tell you that they do exist. Okay. But they are very different and that require a lot of hard work, and we will see eventually. Okay. My Zoom stopped. Okay, so now whatever little time we have, let's try to design some non-oblivious algorithm for these problems. Is that fine? So let's look at the first question. Okay, now we want to do this is no more given to us. This is now oblivious. Okay, so what is our running time should be? What is the thing we can say? Either say that there is no feedback vertex set. There is no feedback. This is what is called feedback vertex set of size at most L, or return a vertex cover of size at most K. Okay, if exists one in f of L time. Okay, can we design such an algorithm for vertex cover, which is an oblivious algorithm?
One way is to like run, we can find approximation, use the approximation algorithm for feedback.
Which we made today morning.
Yeah.
Okay. So, so what is known about this, that in fact, so we did design an approximation algorithm. We did design an approximation algorithm. It is not as obvious as whatever we have been doing. Approximation algorithm for feedback vertex set. Okay. In fact, this algorithm is a factor 2 approximation. But what we did make is like some factor 5 approximation, or even more words, right? Some 7. Actually, we made some 7. Okay. So there is a factor 2 approximation. So what will the running time of that algorithm will be? So that algorithm, we can compute in n to the power big of 1 factor 2 approximation, and then it will run in time 4 to the power L n to the power big of 1. Is that fine? We can compute vertex cover in this, right? Okay. But can we apply the strategy number 1, where can we design an FPT algorithm for feedback vertex set and use that to test whether there exists a feedback vertex set of size at most L or not? I mean, that could also be one strategy. Is that fine?
Yes.
Yeah. So that could be one strategy. Okay, but maybe you will say, okay, anyway, we have 4 to the power L. Why do you care? That's a good point. What about odd cycle transfers? What about, okay, so what about non-oblivious algorithm when parameterized by? When parameterized by, say, modulator to bipartite graph. Right? And this is a problem which is actually called odd cycle transversal. Okay. So input is G S and S. My parameter is S. And the question is, does G have a set S subset of VG of size at most S such that G minus S is bipartite? Is that fine? Do you know any approximation algorithm also for this problem?
So this has no constant factor.
This has no constant factor. Not known, or we can prove that there is no constant factor approximation.
Yes, we can prove.
Okay. So, this I don't know, but like, let's say, according to Saini, no constant factor approximation Unless,
Unless I think unique M conjecture is true.
okay, unless UGC fails, doesn't matter. Like, fine. But is that an end of the road? Is that an end of road, Madhumita? Or some other constant factor approximation algorithm could also be helpful.
Approximation for feedback vertex.
Feedback
vertex.
What?
Like forest is a bipartite graph.
So? But not other way around, right?
Yeah.
So all I'm asking that, suppose we had log-in factor approximation for this, is it helpful? Any log factor Satyavarta is saying, okay? Okay.
It
So
has
suppose,
square root log n factor.
okay, fine. Let's say log n itself. No, it doesn't matter. Suppose alpha is log n. Is it good enough for us?
Yeah, still good.
Why?
Because like,
so look, now our set S, all we can guarantee is that set S that we have is size at most log n times L. Okay. And then if we do 2 to the power mod S times n to the power big of 1, then this is 2 power is that fine? This is equal to
n to the
n to the power n.
Is it still fine?
It's bad, but
I mean, yeah, if L is the parameter, then it's X.
I mean, it's not FPT. I'm not talking about anything else. It's not FPT at least.
Yeah.
But like, really? Is this the running time of our algorithm? There was some reason I wrote something very different. Even though Ajay wanted me to write 2 power L, but I did not write 2 power L. Okay, let me go back. I knew that at some point of time I will need it, but I'm sure everybody ignored it. So I go back. Very first thing I wrote. This is what I wrote actually. Is this fine? Maybe it will help, but like, I don't know. This is what we had. This is our running time of the algorithm, right? Does everybody agrees to this? Right? So now, what will the running time of our algorithm will be? Is this fine?
Yes.
So which is like, can I say this as like, is everybody with me on this? No? Like, how many of you understand this line? Please be honestly put it. +1 if you really understand. If you don't, please ask. Do you realize that n to j is always upper bounded by n power j?
Yes, by binomial.
I don't know about binomial or something, but this is always true, right? Because n to j is upper bounded by enj to the power n, right? So, sorry. Yeah. So it's roughly n to the power j. Yes, no. Please give some feedback. Otherwise, it looks.
Yes.
So now each term is like n to the power I. So I took I, the highest, which was k, and rest of them I put in this, right? But it's a big change. It's no more what we wrote before. Okay. So what is now? Let's focus on s power k. What is cardinality of s?
Log n times L. It was log n times L, right?
Log n time L.
L.
Yeah. So this is okay. So will this work then? This is all that I can say, because it is practically possible, right? Is that k is much larger than L times log n. It's possible, right? So not much can be done, even if I try to save using these things, because you can show that this number is actually upper bounded by, you can actually show is L power k times k power k plus n. This you can show. But like, that's not useful for our purposes, right? So log n is not useful. Okay. But is root log n useful? If alpha would have been, no, I'm just trying to understand, right? Is alpha root log n enough? Because then, what is this? Times this L. Is this good enough? Log n was not good enough, but is this good enough? Two to the power root log n, I cannot write n. 2 to the power root log n, I cannot even write root n. That's even much smaller number. What is this? You understand my question, right? Look, when I had 2 to the power log n into L, you people immediately said n to the power L. But imagine that I have a root log n approximation, not log n approximation. Okay, so I tried all kind of things with log n, and it doesn't seem to be giving us anything better than some sort of XP algorithm, right? But imagine that if alpha is like square root log n, then we are just going to do 2 to the power square root log n times L. Yeah, I'm not able to write n to the power L for anything. Can I say, is this correct? The 2 to the power root log n is less than log n? If asymptotically, is this correct? Actually not true. This is not true, right? Because then I'm saying that square root log n is less than log n, which is not true. Okay. So what is APJP? What is this? There's a difference. What is this arithmetic progression and GP relation? Does anybody remember?
AP is less equal to GP.
I mean, you mean AM is
Yeah.
AM is one.
Arithmetic mean is less equal to geometric mean.
No, it's greater than equal.
If I recall correctly, it is this: x plus y by 2 is greater than square root of xy.
Yeah.
Right?
Yeah.
Is that correct?
Yes.
Okay. So can I try to apply this here?
Maybe y x equal to log and y equal to 1.
What can I say this using APGP? What this is less than equal to?
Oh, okay.
Can I apply APGP here? Anybody? Come on, you people are much better than me in maths. Using this inequality, what can I write?
L plus
What? Can I say this?
L plus by
Is this okay? How many of you agree to this?
yes, it's true.
Okay, excellent. Then, okay, then 2 to the power square root of log n times L is 2 to the power log n by 2 plus L square by 2. Is that okay? Okay. Which is equal to, what is the 2 to the power log n by 2?
Root n.
Okay. Times
2 to the power L square by 2, which is FPT.
which is
FPT.
but if it would have been log n, then it would have been log square by n by 2. Do you understand? Is this fine or not? You might ask that, hey, why did you not try this with log n? Try this with log n. Now, what will you get? What will you get?
2 to the log square n by 2.
2 to the power log square n by log square by n by 2,
Yeah.
which is Yeah, it is like n to the power some square root log n or something. N to the power log n or something, right? Which is not FPT. All right, but okay. But if this is what we are going to apply, what would have happened if it would have been log n to the power, say, 4 by 5? Okay. All I'm saying to you, what happens if this is log n to the power 1 minus epsilon? What will we get then? Will this work then? All I'm asking you, will this work? Like, is it root log n special, or log n to the power half plus epsilon will also work? Little bit more using this formula. I don't know. That's like, I think just after half, it starts to becoming a bit more difficult. Okay. Anyway, so all I'm trying to tell you that root log n approximation is still good enough for our purpose. So if Sani says that odd cycle transversal has square root of log n factor approximation, that implies that vertex cover parameterized by OCT oblivious is FP. Is that fine? So what will we see next time? Okay, on Thursday. So that's an agenda item for Thursday. Okay. Try to design an algorithm for feedback vertex set. Like, I will try to apply the strategy 1 and then do odd cycle transversal. And how will we solve odd cycle transversal? We will solve odd cycle transversal by vertex cover. Okay. So we'll again apply vertex cover to solve odd cycle transversal. Okay, so it will be fun. Okay, is that fine? So that's a plan for the Thursday. Okay, so try to design an algorithm for feedback vertex set if you have not seen one in next couple of days. It's a good exercise. It's a good fun. Any FPT algorithm for feedback vertex. Okay. Okay.